Hi guys, and welcome to the spring semester of AP Physics C. So today we are going to start our discussion on electricity, doing a little review from something that we did last year in AP1. We're going to talk about electric forces, but we're going to go into them a little bit with some heavier geometry than what we did last year. So before we start talking about electric forces, we need to have a quick little discussion about electric charges, what kind of charges exist, and how they move from place to place. So objects can be electrically charged through contact or something called induction, which we're going to talk about in a second. Most of you guys have experienced charging by contact through static electricity. So, for example, if you walk across the carpet in your socks and then touch something metallic or something that's a conductor, you can experience a shock. Well, same thing if you slide down a plastic slide. Sometimes you can scoop up some extra charges that way on your body, or even just getting into and out of your car. All of those examples are examples of static electricity. And in those situations, what's happening is your body is collecting extra electrons from the carpet or from the plastic slide or from the car seat. And so your body builds up this excess negativity. And your body wants to discharge all of those extra electrons. And so they discharge them into the very first thing that your body comes in contact with that will accept those electrons. A lot of the time that something is metallic, like a doorknob or a television set, or it can even be another person that will act as a conductor to accept those extra charges from you. And so you experience a slight shock when those electrons leave your body. So that is essentially how charging through contact works. We'll get into induction here in a few minutes. And this is just a funny picture of a dog with a lot of static electricity in his hair. You also need to be familiar with a concept called conservation of charges. A lot of things are conserved in science and in physics. We have momentum, angular momentum, energy, but we also have charge. And so the amount of negative charge an object will gain is the amount of negative charges the other object lost. So if you scoop up a charge of, -6 coulombs, which a coulomb is the unit of charge here. Oops, let me go back. It's called a coulomb, and this is Mr. Coulomb himself, which is why I put his picture here. So if your body acquires a charge of -6 coulombs, which is a lot, that represents how many electrons or how much charge the carpet lost. So you're not going to all of a sudden gain more electrons or more charges than the object that you're taking it from. And this number right here is going to be super important. Let me go back one more time. Not yet. Okay. This number is going to be super important for your math. It is on your formula chart on your list of givens, but you'll probably end up memorizing it anyways. This is what we call an elementary charge, or the charge of an electron and a proton, because of course the charges on these two are equal, just an electron has a negative charge and a proton has a positive charge. So 1.6 times 10 to the -19th coulombs. Okay, so let's have a quick talk about what induction is and why we use it. So induction is a way to charge a conductor, because when you think about it, in the case of charging by contact, all of those examples use some kind of insulator to acquire the charges from, right? Carpet is an insulator. A plastic slide is an insulator. These are not metallic objects, which is what we typically think of a conductor to be. If you guys have ever rubbed a balloon in your hair, again, that is a insulator collecting or distributing charges. So conductors have to be charged through a way called induction. And what we're going to do when we charge a conductor, if we want to give a piece of metal an overall charge, we're going to induce that charge on it, hence the name induction. So we bring a charged material close to a conductor. We don't actually touch it to the conductor. We just bring it pretty close to it. And then that creates what's called a charge separation, which I'll show you guys on the next slide, a picture. Once that charge separation is created, we can ground the conductor, which means connecting that conductor literally either to the ground or to another larger object that will accept excess charges. And it creates like a sink, and it leaves an overall positive or negative charge on your conductor. So let me just show you guys a graphic as to how this works. So here we have in picture A, we have an initial uncharged piece of metal. It's just completely neutral. And then in picture B, I'm going to bring this negatively charged rod or object close to my conductor and then look and see what happens. My conductor, the reason why it's a conductor is because charges can move really easily through conductors. So they move around, and it's what makes a conductor a conductor. So as this negative rod gets close here, all of the positive charges that are in this neutral conductor want to get really close to it because opposites attract. This is something you guys probably learned in chemistry. We talked about it a little bit last year, but this idea that negative and positive charges will attract one another, and negative charges repel one another. Very fundamental law, I guess, in chemistry and physics. So positive and negatives want to come together, so this is going to create that charge separation that we were talking about. Now that I have this charge separation happening in my conductor, what I can do is ground my conductor. In this case, they connected a wire to my conductor, and then in this case, they literally put it in the ground. But it might not be in the ground. It might be connected to something larger, or you as a person, you might act as the ground if you were to touch this piece of metal. But it just gives those negative charges a little bit further to go. Because now, here they tried to get as far away as possible from this negatively charged rod, and as far as they could go was the other half of the conductor. But if I connect a ground to it, now they have a conduit or a place that they can go that's even further away from this negative rod that they don't care much for. So connect to the ground, the charges flow into the ground, remove the ground, and then what I have, essentially, is a positively charged piece of metal. And here, on the last slide, I have I can remove my negatively charged rod, and then I have a positively charged piece of metal, and these extra electrons are in the ground, where they don't contribute really any overall charge to anything, because the ground is so large. So this is the process of induction, and it's important to understand the concept of how the charges move and where they go and why they go there. So I wanted to make sure you guys had a little review on that. Okay, so here's another kind of example about a charge movement. So in this one, they're saying we have two identical conducting spheres. Ooh, let me go back. We're not there yet. Two identical conducting spheres, one with an initial charge of plus Q. So here's one, and then here's the other one, and this is plus Q. And then it's going to say this has a charge of 0. They're going to touch one another. So because they're conductors and they come into contact with one another, those charges can move really easily between conductors. So what's going to happen is that some of these positive Q charges will go and move over to this second object because they are conductors and they are touching each other. So part A says, what is the new charge on each sphere? Well, if I have plus Q and I touch it here, these charges are going to redistribute themselves equally and evenly between these two spheres because they are identical. We'll get more into situations where they might not distribute evenly later. But in this case, because they are identical spheres, and there's plus Q, well, now that plus Q has to be shared between both of them. So each sphere will get 1/2 Q in charge. So the spheres are touching, and plus Q here. Oh, sorry, plus 1/2. Ah! And then we're going to bring a negatively charged rod So here's negative, 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 close to one of them. And that will cause it to have a charge of plus 2q, right? If this is negative, what do the charges want to do? Well, all of the charges want to come together on this side closer to this negative rod. And this is all just a hypothetical situation. I'm just asking this question so that you guys can understand kind of charge balance and charge movement. So, another... what the heck? There it goes. So now we have a rod here, and now this one has a charge of plus 2q. So they're asking if this object now has a charge of plus 2q, what is the charge on the other sphere? Well, we started with 1, right, plus q. So consequently, the total charge here for these guys still has to be plus 1q, which means in order for that to happen, this sphere has to have a charge of negative q. Right? So we haven't really gained or lost any charges in this scenario. They've just kind of rearranged themselves. The positives that were on this guy kind of went over to this guy, and now we have a total net of plus 2 on this one because this is the one that's closer to the rod, which means that in order to have a charge of plus q, which is what we started with, this guy has to have a charge of negative q. All right, so all this is leading up to the math in this little section, which has to do with what's called Coulomb's law. And Coulomb's law is a way to calculate the electric force between two charges. So the electric force between two charges can either be positive or negative, attractive or repulsive. So if I have a positive charge and a negative charge, this is an attractive force. These two charges will want to come together. If I have positive and positive, this is a repulsive force, which means that these two charges will want to push away from one another. And that direction becomes incredibly important when we start looking at multiple charges, which we will do on the last example. So the last little thing I want to make sure you guys kind of understand is that this law follows Newton's third law of motion, which says that the force that one exerts on the other is equal. So we'll get into situations where this kind of comes apparent later, but just keep this in mind when I'm asking you questions about what is the force on this guy? What is the force on this guy? Well, if they're together in a system, the force that's on either one of them should be equal. All right, so let's look at an example using Coulomb's law, which you guys should have done last year. And we're going to find the force between 2 point charges. So this one has 2 point charges here and here, and they're both 0.05, and that U is microcoulombs. It means 10 to the 6th. And they are separated by a distance of 10 centimeters, but we always want to make sure that we put this in meters. So these are two positive charges, so they are going to experience a repulsive force. So this guy is going to experience a push this way, right? This would be my force vector. And this guy is going to experience a push this way. That would be my force vector. So, part A, find the magnitude of the forces exerted by 1 point charge on the other. So, we're going to use Coulomb's law. KQ1, Q2 over R squared, which you guys had on the previous slide. K is a constant, 9 times 10 to the 9th. Both of these charges are the same, so I'm just going to do 0.05 times 10 to the negative 6th squared. And then you just divide that by 0.1 squared. So this example is pretty plug and chug. Whenever you have 2 point charges like this, it's super easy. And the answer I get is 2.25. And you guys can either put times 10 to the negative third newtons or millinewtons. I guess millinewtons is not a very common unit, but the force that you get from 2 point charges is probably going to be pretty tiny. This electric force, because the charges are typically really tiny, is not really a huge number a lot of the time. Okay, so part B says, what is the net force on a +1 plus 0.1 microcoulomb charge midway between them? So now let's see if I can't change my ink color and get a different here. Okay, so now exactly halfway between these two, 0.05, 0.05, we have a 0.1 microcoulomb charge. So all of these charges are positive, so let's look and see the vectors, draw the force vectors here. This guy, between this guy and this guy, these two charges, he will experience a push to the left. And between this one and this one, he'll experience a push to the right. So since he's in a situation where these charges on either side of him are equal and he's exactly in the middle between these two charges, his net force that he'll experience will be 0 newtons. He'll want to go away from both of them, but since, like I said, they're both equal, the distance between them is equal, it's going to end up being 0. Okay, so let's look at 3 charges and put this together here. Q1 is at the origin, so here's Q1. Q2 is over here at 2 meters, and then Q3 is over here at 3.5. So x equals 3.5. So here is 2. Now the distance from here to here is not 3.5, it's 1.5. I kind of drew that a little too big. Not drawn to scale. So find the total electric force on Q3 due to Q1 and Q2. If Q1 is 25 nanocoulombs plus, this guy is negative 10 nanocoulombs, and this guy is positive 20 nanocoulombs. Okay, so in all of these examples, the very first thing I like to do is to draw my force vectors. Right now, in these charges in a line, it might be a little bit easy to see, and you think you might not need to do it, but when the geometry gets tricky, like when we're talking about squares or triangles or anything else like that, you want to draw the force vectors just so you can see what's happening on the charge that you're concerned about. So here on charge 3, he's experiencing 2 different forces. An attractive force between Q2 and Q3, and then a repulsive force between Q3 and Q1. So his force vectors here will be a push. And I like to write the force on 3, 1. And in physics, this means the force on 3 because of 1 is going to be this push to the right. And then he's going to experience a force, a pull, force on 3 because of 2 to the left. All right, so what I'm going to do, since I've already drawn the force vectors, is I'm going to calculate the magnitude of these forces. Some people get thrown off by the negative, positive, and the charges and stuff, but I kind of feel like I've already taken into account the positive-negative situation because I've drawn my force vectors, and I can see